All right, welcome everyone. This is another in our continuing series of Smart City podcasts hosted by ARC Advisory Group. I'm Jim Frazer, the Vice President of Smart Cities here at ARC. I'm joined today by Eddie Fidler, who's another colleague of mine and an analyst in the transportation and energy domain. But our guest today is Rick Rys of ARC. He's a senior analyst here at our organization and focuses on energy technologies and applications. So Rick, before we formally get started, could you tell us a little bit about your background and what you do at ARC, maybe some recent studies you've completed?
Sure, thank you, Jim. So my background is as a chemical and electrical engineer. I worked for 3 years at a chemical plant in Niagara Falls that took salt water and electrolyzed it to caustic chlorine and hydrogen gas, kind of a battery in reverse. I worked for 20 years, though, in Foxborough Company in Foxborough, Massachusetts, as a control system design engineer, where we designed, built, and implemented, executed, started up control strategies in a wide range of industries: oil and gas, power, pulp and paper, food, pharmaceutical. I left my job at Foxborough and became my own one-man consulting company in 1996. And I continued to work in those very same industries. In fact, I also left under very good terms and continued to work for the Foxborough Company, which by that time became Invensys and then Schneider Electric. And I worked in a number of oil and gas projects for them, as well as many other directly clients. I also had the chance to work for several years on nuclear power plant control systems, including the whole balance of plant and the emergency shutdown systems. But for the last 4 years, I've been a consultant at ARC. I've worked on market studies for ARC in the area of operator training, HVAC controls, system integrators and automation suppliers. I also executed studies for microgrids, grid-scale batteries, and transmission and distribution SCADA systems. So that's pretty much my background. I should also mention that I had a few other kind of things outside of my direct professional life. I designed and built my own solar net zero house, which also includes is all electric. Also includes an electric vehicle, so I have some experience with that. And I'm also the light commissioner in our small town of Princeton, Massachusetts, where we have to maintain the entire distribution system. So I'm very much involved with maintaining a real electric distribution system for people that complain when the power goes out.
That's fascinating, Rick. I also know that you recently completed some work on autonomous vehicles as well.
Yeah, somehow I've got to be one of the primary go-to people for drones, drone automation, and as you get into the autonomy issue of drones, some of the same type of issues show up. In fact, some of the more different issues show up for autonomous vehicle activities. And of course, having a car that has the enhanced auto drive capability, I have some firsthand experience to see how each new software release improves upon the previous one. And so very interesting to see what the future will hold, and that autonomy will make a huge difference in the future.
Wow, that's fascinating. Hey, Eddie, I see that you have a question.
Yeah, for sure. Well, thanks a lot, Rick, for the introduction. And I figure we'd start with the electric grid. So there's a lot happening in the power gen, the utility sector. Can you talk about some of the disruption that the grid is seeing and where that's coming from and where that's going?
Yeah, great. The grid is definitely in a high state of disruption compared to other industries. One of the key issues is that economies increasingly depend on power. I could imagine that most everyone listening to this podcast would have some difficulty going without power for 3 or 4 days. So hurricanes like Maria that caused a lot of damage and put power out for a long time really hurt a lot of people. And so there's always been an issue, though, of cost and cost and reliability issues. And also the other disruption is that a lot of places in the world that never had power before suddenly have power. China and India claim to be nearly 100% powered. The only continent on the planet that's got some issues in terms of power distribution is really Africa. The second disruption is the grid power sources are rather disruptive, and so there are some problematic issues in terms of how we've built our electric grid to date. We see coal and nuclear being displaced by lower price natural gas, and then natural gas in turn being displaced by lower cost solar and wind. And then the third main issue is really environmental. There's an effort to reduce CO2 emissions across the whole board, which means the large CO2 emissions from transport and buildings really need a non-CO2 emitting generation source. So these things are impacting the type of new resources going onto the grid.
Rick, this is Jim. So you started talking about some of the larger issues driving generation and distribution of electric power, but maybe can you drill down a little bit into the impacts of microgrids, of off-grid generation, and maybe even some efficiency issues of, say, the impact of LED lighting on public infrastructure?
A lot of issues. When over the last couple of decades, we even see this in our own town, is the amount of electric power we've consumed here in the U.S. has been in decline. So that's been in decline because of some of these efficient appliances and more efficient utilization, and really that conservation and efficiency has been awesome, all right, and has reduced the demand for electricity in countries like the U.S., where China and India getting electrified for the first time, their demand has soared. Going into the future, we would also see that there are likely to be increased demands. If you try to electrify transport, if we start moving from internal combustion vehicles for cars and trucks, and instead of heating with oil and gas, you're heating with heat pumps, etc., the projection for electric power consumption in the future for the U.S. is increasing to a large extent with how fast these new technologies impact transport and buildings. The efficiency gains that we have made, LED lighting is certainly a case in point. The thing is that an awful lot of places are fully LED lit, and so they've gotten those improvements. I'm not sure that there's a new technology that was quite as impressive as going from incandescent to LEDs going in the future, maybe slightly more efficient LEDs, and there are probably a lot of other lighting technologies. So those are some of the things. Now, as far as the microgrids are going, we can talk a little bit more about that. I will mention that the whole issue on the electric grid associated with regulation or deregulation plays a big role. There's a lot of grids that maybe the country, the grid controlling entity is kind of a country or a government, and they just manage the entire grid, or there could also allow a number of players to become generators and participate in the grid management. For example, we saw the FERC in the U.S., the ERG organization, FERC, Federal Energy Reliability Council, was FERC, has a FERC Order 841 basically started to allow grid scale batteries, for example, to compete in the wholesale energy market, and suddenly that's opened up a lot of opportunities for grid scale batteries.
Well, Rick, on this issue, can you, I know that particularly in Europe, that ownership is a bit more diverse, and as a result, a number of standards have developed there and are quite more advanced than we have here in the U.S. Could you talk about the standards in terms of, say, IEC 61850, and maybe some of the other standards in the area, like for automated demand response, like OpenADR 2.0?
Sure. One of the things you'll certainly see in our current electric grids is there's a lot of existing infrastructure that is very durable and lasts a long time. So, in our substations, we see a lot of older equipment, and that older equipment is in many ways serviceable. The things that do happen is, where you're putting in brand new substations, it's relatively easy to go to a standard like the 61850 communication standard that could reduce a lot of the wiring costs, allow you basically to put fiber optic devices right to the end devices, things like reclosers and synchrophasers and all of the other electrical switchgear could be directly wired rather than wired analog signals into an RTU, MTU infrastructure. So the digitalization of substations and even the whole distribution network is very important. Obviously, to manage an entire distribution system requires the ISOs, the independent system operators, regional transmission operators. There are people and control systems looking at the entire network and identifying a number of issues that need to be addressed, all right, to efficiently dispatch electric power. And so part of that efficiency is, and we'll get to demand response in a bit, is it kind of goes back to an MIT study some years ago that basically said the spot price of electricity can be varies by depending on the location and the time, and as a result, that deregulation resulted in the utilities trying to drive the electric power management economically by every 10 minutes, for example, here in New England, ISO New England computes the local marginal price, and that local marginal price has a great driver on power. If that marginal price is very high, some manufacturing plants could decide to defer production if they have the option to do that. If in some cases the local marginal price technically goes negative, it did this very recently here, and actually you are fined for consuming for generating electricity. All right, you have to pay. You would be paid to use electricity. These situations don't happen very often, but all of these issues associated with the management of the grid are very critical and important. Demand response is a whole nother issue, in the sense that currently the electric grid started to be regulated by what's called AGC, automatic generation control, which is basically looking at the frequency of the grid. Very small grids could be regulated by voltage, but large grids are basically regulated by frequency. And the frequency actually changes depending on the load. A lot of loads come onto the grid. Instead of running at 60 cycles, you're running at 59 and a fraction. All right? And all of the spinning reserves on that system were, have built-in governors that will act to compensate for that load. Some plants, like nuclear plants, can only act in a very short term with just the spinning inertia of their turbines, but others, like natural gas, can actually bring on more resource. Natural gas and coal can burn more fuel to match that load, and so these dispatchable generators are part of that system.
Rick, that's interesting from the perspective of the power generating entity. But can you comment about the spot pricing impact, not only on industrial plants, but here in North America and in Europe, you do have some larger scale owners, let's call them. We have a range of municipally owned utilities, rural electrical co-ops that represent one large load. Does that spot pricing also impact them as well?
The ISOs have actually a list of phone numbers of the major manufacturers that have discretionary loads, and when there becomes capacity issues on electrical networks, there are in some cases prearranged relationships so that the numbers of industrial and maybe large commercial units will defer load, or so they are participating in the management of the grid, and which, by the way, the grid must precisely match the amount of power being generated with the power being used. Very small mismatches. Would anything beyond a small mismatch could end up tripping the whole grid and have a blackout. So the thing is that already we've seen for quite some time that industrial and commercial users are involved in that, and to some extent they are motivated by the local marginal price. So there's a price mechanism that's involved. In other cases, they are just, look, we need you to shut down. And ironically, some of that is done by ordinary phone calls to people saying, we're anticipating that we have a big load coming up. We need you to either to generate or to cut back. All right. And so there's a dispatching function in the grid management systems. Now, the other interesting thing is that if we look at going forward, if in fact transportation and buildings become increasingly electrified, there will be a very big necessity, for example, to involve them in a demand response point of view. That in many cases these smaller facilities, individual residences, small buildings, and even many office buildings are not really part of the electric grid load management, even though they may have some discretionary loads.
Well, it's interesting. I'd like to ask you then about, I know that the Department of Energy quite a few years ago went to ASHRAE, the American Society of Heating, Refrigerating, and Air Conditioning Engineers, and they issued, I believe it's published, I saw the draft a while ago, basically an energy services interface to larger building campuses. And as a result of that, some of the work I had done before I joined ARC was developing a similar but much lighter, call it an energy services interface, to the public infrastructure on roads, meaning lighting and traffic signals and whatever else might be out there, rest areas, toll booths. What's really the maturity at this point in time of automated demand response?
I would say that is relatively immature. In some of the things that we've investigated here at ARC, we kind of refer to the entire problem of how to manage the electric grid in this regard of supply and demand, and involve the increasingly important smaller users. If you have a lot of individual residents with solar panels and individual residents with batteries, individual residents with electric vehicles or truck or bus charging stations, and or buildings that could store energy thermally, these organizations are not typically connected here. This has kind of been described by some as the largest system integration problem of our time. The ISOs that are running those grid do not want to make specific power purchase contracts with every single residence. So there needs to be this intermediate layer of aggregators that can collect and organize a number of people in smaller distribution systems in order to bid into the markets for wholesale price of power, the day-ahead market, even the frequency control market. There's all of these different markets that can be participated in, and many of those markets are just not open to small players today.
It's interesting. I've heard it described that the electricity industry really is moving from arguably, generating the power and counting the electrons at the end of the line, to really managing a peer-to-peer network of intelligent devices, and actually just simply managing electron flow between devices on a network, more like an ISP. I could see the challenges that you bring up in terms of frequency matching. If I'm feeding power from my small microgrid into my network, as well as what if me and my three neighbors all have electric vehicles and we all would like to charge at the same time on the same transformer. I could imagine that some difficulties will result.
Let me kind of comment on that. As there's already been a number of disruptions that I mentioned in the past, where non-dispatchable generation assets like solar and wind, are put onto the grid, and solar in particular in places like California and Hawaii, have started to be so prominent during the daytime that pretty much all the other generation assets on an electric grid are throttled down to the lowest possible operating point. This is the famous duck curve relationship by CAISO, the California ISO, that basically shows that during the day the amount of solar being generated is so high that, and then as soon as the sun goes down, what has to happen is there's no more solar, and all of the more conventional dispatchable generation like natural gas plants suddenly have to ramp up at an unprecedentedly high rate, and so as a result, they will. California and Hawaii and others have kind of tried to maybe encourage energy storage for those people that are putting in solar in the future, so that they can shift that generation interaction with the grid from, instead of dumping solar power into the grid all during the day, they store that power locally. They don't dump it into the grid, and they also remove power from their batteries at peak load times, roughly 5 to 9. So there's these three curves that I was mentioning. I suppose I should mention. One is the duck curve, and that's basically the curve that occurs from solar generation dominating the generation of a network. The second one is, I think you kind of touched on it. Let's call it the dragon curve. Individually, the dragon curve is not exactly what the one you mentioned. The dragon curve is basically these high voltage DC chargers, of which a single vehicle put onto the grid makes, suddenly starts consuming 300 kilowatts of power, right? And so that puts a significant spike in a small distribution system. It's not really a problem for larger transmission networks. But then there's the third curve, which is a little bit more problematic, and let's call this one the shark fin curve. And basically, it implies that if we suddenly get a lot of electric vehicles on, in common use every day, and everybody's going to work and coming home at 5 o'clock, and everybody plugs in their electric car at 5 o'clock, the time period between 5 and 6 shows a huge ramp up in power. So collectively, the individual car chargers at a residence, they're only level 2. They're nowhere near 300 kilowatts. They're closer probably to 8 kilowatts. These things collectively, with hundreds or thousands, or potentially millions of cars plugging in at the same time, will put a big problem into the electric grid. All right, and basically could in principle cause blackouts. But on the other hand, they also could become quite a resource for evening out the grid, and I'll bet that probably Eddie has a couple of questions on that.
Yeah, well, Rick, that's very instructive. That's a very instructive view of the entire generation and distribution architecture and a lot of the issues surrounding that. Let's drill down into some of the components of that network. I know Eddie's got a question. Go ahead, Eddie.
Yeah. So I want to pick up on a lot of what you said there, Rick. There's a lot to digest, and it's quite fascinating as always. So you mentioned the renewables piece here, where renewables like solar and wind are intermittent. So I just wanted to see what is your opinion on a reasonable roadmap as we necessarily have to increase the levels of renewables, and how do we properly integrate that? Do you see nuclear? Do you see natural gas with carbon capture as options here, or for the medium term at least? What are your views on that?
So that's kind of like the world's toughest problem these days, But I think that ARC has done a lot of work here, so we do have I think a little bit to offer here in terms of being able to look at so many different industries and how they're automated and how they interact together as a unit. We certainly see that coal and nuclear are having a difficult time competing with natural gas. If you start adding all the stack gas scrubbers and things on coal plants, they can become pretty expensive to operate. If you were to ever get a tax on CO2 as a pollutant, coal plants would be just absolutely non-competing. So coal plants are being shut down left and right. Right. Nuclear is a whole nother issue. Nuclear is certainly non-emitting, and you would think that, and many people would think that nuclear would be a great way to expand our base load and be able to get a carbon-free electric grid. And from that perspective, they would be. The only problem is that ever since we had the Chernobyl accident and then the Fukushima accident, and we've had a few other problems in the nuclear industry with regards to, as a result of those accidents. There's been a lot of new regulations. For example, the Atomic Energy Commission came up with a number of new expensive regulations that require the nuclear industry to deal with additional compensating measures so that they could tolerate the type of accident that occurred at Fukushima, which was a total station blackout. And I don't think that we had necessarily been adequately prepared for that. And at the same time, we see that although initially there was no tax on carbon dioxide or things like this, carbon tax, but there was a lot of incentives given to solar and wind. And those incentives have resulted in multiple generations of solar panel manufacturing technology, the economy of scale of that, and certainly in the wind turbines, we've gone through 4 or 5 generation of wind turbine. The blade regulation, the gearboxes, in some cases without gearboxes, and then finally the generators or converters that the wind turbines are using. So the wind and solar prices have gone down so low that they're absolutely much more competitive than coal and nuclear, and in fact today even potentially quite competitive with natural gas, possibly even competitive with natural gas as a peaking asset if you would consider solar and wind along with storage. So obviously then one of the biggest problems we have if you start moving to non-dispatchable renewables like solar and wind is you need to start balancing all of those out. There's a whole range of possibilities now that come into play, and obviously there's been a lot of press recently on a lot of battery technologies. There's a tremendous amount of grid scale batteries that are available now. You can buy them from all kinds of different suppliers, including the instrument and control suppliers have battery packages available, in the megawatt time frame. I think it was also PJM ISO area here in the Central Atlantic here was helped to prove the concept of lithium batteries being useful for frequency control, and therefore that helped to take up the slack from spinning reserves. So we're seeing spinning reserves from the coal and nuclear getting replaced by grid scale batteries that can handle those very fast responding frequency controls. The problem though with lithium batteries is that they get to be very expensive once you start getting more than a few hours of storage. So we still have a big problem of storing power for days, weeks, or hours, and pumped hydro is obviously an option, and even conventional hydro operated as a storage asset has some potential in the future as well.
Oh, okay. So I wanted to drill down a little bit about those economics. So you're saying that the price of wind and solar has plummeted, and so it's competitive with even nuclear, even gas, but that's only as an intermittent resource. When you consider the price of energy storage, do the numbers still stack up, or where do we stand with that?
Well, some of the big energy storage products we've seen come in here, and we've got a number of utilities in our area that have put in lithium batteries. They put in those lithium batteries to typically they're going after the transmission and capacity costs. All right, so those things have generally had a pretty good payout. There've been some subsidies and government subsidies here in kind of the state level at least, and of course there was lots of subsidies here for solar and wind in terms of tax credits, and particularly the production tax credit for wind. But the battery issue is an interesting one. We see a lot more batteries go out there. We see a few people putting flywheels in. We see a lot of activity going in the flow batteries, which have the potential promise of being a lower cost. The cost structure of lithium is they're always talking about this $100 per kilowatt hour of storage, and we're getting down close to that. But still, even at $100 a kilowatt hour, we don't have enough economics to justify, to handle a grid that starts to get dominated by non-dispatchables.
Okay.
Mm-hmm. One thing I wanted to mention is that one of the other solutions to this is to interconnect grids to be a larger grid. So we see a lot of high voltage DC transmission. We've seen we need to be able to move power from where it's generated to where it could be used. In the U.S., we have 3 isolated grids: the Eastern, Western and Texas grid, and obviously we're not even connected to the Canadian grids or the Mexican grid. So one larger grid would be much more stable and would allow the opportunities to move power generated at one location to others, and that would go a long way as, in many cases, a more economical opportunity than putting grid scale batteries in.
And that's even given the power losses over long distances.
Yeah, that's true. I mean, lithium batteries do have the advantage that they have a very high efficiency rating. The round trip efficiencies in the mid 90s, I think. Some of the other battery technologies, the vanadium redox flow batteries are down in the 60%. Pumped hydro is in the mid 60%. And there's still other options of hydrogen, ammonia storage, and a number of other different kinds of flow batteries. I would mention that one of the things that also I think is going to have a big impact is the amount of lithium batteries being made for the electric industry will pretty quickly dwarf the amount of lithium batteries being made for grid storage. And with all these lithium batteries driving around on the highways, the utilization of those lithium batteries to interact with the grid in a more interesting way, but in particular, I would mention vehicle-to-grid technology, has a big opportunity in the future that we're not currently taking advantage. None of the electric vehicle manufacturers are supporting vehicle-to-grid in the U.S.
Rick, this has been just a superb overview and in depth in some parts of the distribution and mechanics and economics of the electrical infrastructure. Can we spend the rest of our half an hour on the components and software platforms that compose this whole architecture? And I'll start with what's a microgrid and what's the value to end users of a microgrid?
It's a very good question because to some extent, we're all familiar with microgrids for a long time. Before solar and wind and common usage of the term microgrid was used, you have a built-in microgrid if you got a little gasoline or diesel generator. I mean, that's a standalone voltage regulating microgrid that can handle a load, adjust the fuel use to that. But we're not normally considering that a microgrid. In our studies of microgrids, ARC tended to focus more on the microgrid control functions. In many of the microgrid market studies, for example, you would see that the revenue of a microgrid would include the revenue for the wind turbines, revenue for the solar panel arrays out in the fields, whatever, and revenue for those types of generating assets, and I suppose including gas and diesel generators. But a microgrid basically has you could argue that the island of Hawaii is a microgrid, but really that's a major grid. So we tend to think of microgrids as something that might be under about 100 megawatts. And some universities are up to that scale of 100 megawatts, where they basically could operate autonomously, disconnected from the major grid, provide all their own power to, possibly with some load shedding here and there, but they could provide all their own power and operate as their own independent entity, generating their power, storing their power, matching their power sources to their loads. And a critical characteristic of a microgrid is typically to be able to interconnect, although it doesn't have to interconnect, but most microgrids are interconnected to the grid, particularly a microgrid that is formed by a renewable asset will often have more generation than they can their loads require, and therefore would export power to a regular grid. And they would like to be able to do that smoothly. In other words, if the main grid goes down, they smoothly take over and power their own loads. When their local renewable generation is too low for the loads, they consume all of that local generation to supply their loads and import any additional amount they need from the grid to match, to keep their load satisfied. So the characteristic of microgrids, tend to support a large number of different situations. On the control layer, though, if you really want to get down to the compartmental level, we talk about three levels of controls for a microgrid. We talk about the primary level. This is the protection level. This is where safety relays and reclosers and fuses and switchgear are involved to keep everything safe. If you have a short circuit, those breakers should open and confine the blackout to as small an area as possible. Right? So there's one layer of controls. The secondary layer of controls that is typically involved is in load management and the control of distributed energy generation, storage and the load. So there is load centers involved. This is kind of at the inverter level. Many of the inverters include a lot of the functionality to do here. The inverter can be configured for a grid-tied configuration or a grid-tied with backup configuration, and the inverter knows about all of these levels of control. Then there's a kind of a tertiary level of control where a microgrid asset might interact with the grid, and this would be particularly true of larger microgrids, that it might be looking at the local marginal price and deciding when to generate, when not to generate. It might also be looking at the peak load on the electric grid to know what the transmission and distribution, because if a microgrid could avoid consuming grid power during a peak load event, it could save a tremendous amount of money on their transmission and distribution costs, because transmission and distribution costs are typically arranged by the 1 hour period throughout the entire year that you've used the most power in your distribution system will go a long way to determining what your transmission and distribution costs are. And these can be 5 or 10, even 15% of your total electric bill. And by this kind of management level, you could make those kinds of reductions. You could substantially reduce the cost of electric power, because if you can demonstrate that you do not need a massive wire from the grid to your distribution system to support your load, because you can shave these peaks off with your microgrids, then there's a lot of money to be saved.
Wow, that's fascinating. So how do microgrids manage the grid stability?
Well, on the one hand, a lot of the justification for microgrids is kind of this concept of resilience. All right, that basically means if you're the local load out in Puerto Rico, this one area of Puerto Rico that hasn't had any electric power for 1 year, and suddenly you've got your own microgrid operating possibly with batteries and a diesel generator at the hospital or the police station or whatever critical asset you have. But nevertheless, if that local load is there serving you, from your point of view, you have some power. All right, you have a resiliency for the power. So there's quite a bit of value in that regard, where a microgrid can provide stable, reliable power even when the main grid goes down. So that's kind of from the perspective of the local load. Now, how can the microgrid help the main grid? And that really would be by responding to price signals and interacting with that. In principle, a microgrid could participate in the frequency control market, in the wholesale market, and provide power when the grid needs it. A microgrid in a major office building that has the possibility, for example, some office buildings will make ice in a large reservoir during times when electric power is cheap and available, and when peak loads occur, they will utilize that ice to air condition the building, rather than use electric grids. So you can see that the interaction of these loads and microgrids with the main grid is kind of a collective thing, especially where the microgrids tend to be relatively small. But there's some fairly large microgrids that could have a significant impact, and collectively a large number of microgrids could interact with an overall grid to produce a stable thing. It does require a bit of system design to make sure all of these microgrids are behaving in the same way, and I think there are some standards that address that.
Thanks, Rick. Eddie, I think you have a couple of questions on energy storage.
Yeah, for sure. So, Rick, obviously the main focus when people talk about energy storage is lithium, and we've talked about that. So you did mention flow batteries, and you seem to think that they're quite promising. So could you give us an intro to what flow batteries are and why the economics might pan out there as opposed to lithium?
So, right, everybody's familiar with the local, D cell, AA cells. The number of batteries that I have is in the hundreds. I have hundreds of these small batteries all over kinds of my electric gadgets of stuff. So these are basically a solid electrolyte. The chemical reaction occurs, and once the chemicals convert from one a kind of a situation to a different electron configuration, so that once those chemical reactions occur and energy is released, those batteries are dead and you throw them away. All right. Now, a flow battery is a little bit different. Basically, you can think of a flow battery as being a fuel cell. Fuel cells consume hydrogen and oxygen that flow into it. For example, there's the Toyota Mirai is a hydrogen fuel cell vehicle. So basically that hydrogen fuel cell is what's called a flowing battery. It has a flowing electrolyte that flows in. The electrolytes in this case would be hydrogen and oxygen. Now there's a number of other flow technologies that exist, in stationary batteries. I recently toured a vanadium redox flow battery from a local startup here in Massachusetts, and there's a number of other companies that are going in there. And basically they have they have a stack, all right, what's so-called a stack, an electrolytic stack, where liquid flows of two different vanadium valences, one, I think, vanadium +2 in one tank and vanadium +3 in the other, and it takes energy to move from one to the other. And as they flow, as electric power is brought into that grid, they basically convert all of the the vanadium ion components into a different valence charge, and that has an energy storage in a water solution of vanadium, and they can reverse that at any time, all right, and suddenly consume that. And so the power generation depends on the size of the stack. The energy generation, however, depends on the size of the tanks to store the liquids. And so this has a huge scaling factor compared to lithium batteries, which are, for twice the storage capacity of energy, you pay twice the price because you need twice as many batteries because the whole battery is stored in the battery. But in a flow battery, for twice the energy content, you just need bigger tanks, and you don't need the difference in the stack. But vanadium redox flow battery that I looked at had very fast response. They actually said they could compete in the frequency response market, all right, mostly because of the way the inverters were arranged, that they could immediately change between generating and consuming power. So at a very fast rate, these are still a kind of, I guess you call it an emerging technology. There is a definite competition. There's almost a half a dozen vanadium redox flow battery companies with different patents and intellectual property that are kind of competing to get a foothold. Their disadvantage, of course, is that they don't have the advantages that lithium has in terms of manufacturing production level and the economies of scale of producing these things at scale. So the first lithium batteries you could expect to be a little bit expensive, but there certainly is the potential that a flow battery, even though it's way too heavy to put in a vehicle, for example, would be a viable solution for electric grids, beyond 4 hours of storage. Lithium is kind of limited to about 4 hours worth of storage for economics, but vanadium is say they want to start at 4 hours and maybe go to daily. Certainly daily storage is a target for vanadium. In other words, all the solar power you could make in the day could be stored in a vanadium redox flow battery and power an entity over the whole night until the next sunny day.
Wow. So maybe not so much that it'll be a winner take all with technology, but maybe lithium is better suited for a certain segment of the storage market, and the vanadium for another.
Well, I mean, obviously, lithium is become very ideal. It's certainly tending to dominate all the electric vehicles. For example, there's, with a few minor exceptions for very high power ranges of things like supercapacitors, and obviously there's also a range of 4 or 5 different chemistries of lithium, and a lot of advancements in the cost of producing a cell. The amount of cobalt going into lithium batteries has been dramatically reduced, and there are lithium batteries that use no cobalt. All right, and cobalt was one of the more expensive components of a lithium battery. And then there's a lot of issues, of course, with lithium recycling. We all know lead acid batteries, and if your car battery is dead, you bring it into the auto parts store and turn it in, and they recycle that battery, and you get a new battery that was made from recycled batteries. That infrastructure is not yet in place for lithium, but there's certainly being worked on and developed, and it's a little bit harder to recycle lithium than it is to recycle lead.
Okay, I see. I think the other topic that comes up, you mentioned, if you're in a sunny area, you're producing solar power all day, you might want to store that for later. There's a lot of talk around using electrolysis and using hydrogen as a storage mechanism, and then using that hydrogen as the basis of a fuel for transport or for industry or something like that. What are your thoughts on that approach?
Well, hydrogen is a very unique substance, all right, and has a tremendous amount of energy storage, all right. In fact, one of the interesting puzzles I often give to people is, why is it, and you'll find why it's related. Give me a minute to show how this flows together. Why is it that most of the fuel in your car is not in your gas tank? And immediate people's response is, what do you mean? All the fuel's in the gas tank. There is no other fuel. Well, you're wrong, all right, because you're driving through your fuel. Those cars, gasoline and diesel cars, do very poorly on the surface of Mars or the moon where there is no oxygen. And in fact, roughly 3 pounds of oxygen from the air for every pound of gasoline, goes into that car. Right. Now, if you have a hydrogen-powered car, that difference is instead of carbon, which weighs 12 plus 2 oxygens at 16 molecular weight each, you have, oxygen weighs 16 with hydrogen at 2, you basically have 8 to 1, 8 pounds of oxygen for every pound of hydrogen consumed. So hydrogen has the huge advantage that it doesn't have to store most of the fuel as the hydrogen. It unfortunately has this huge disadvantage that its energy density is so low that it's really hard to put it in a small volume. If you needed to have a hydrogen-powered car with gas at atmospheric pressure, you'd need to tow a blimp, all right? And the Mariah has to put very high pressure, carbon reinforced tanks. But for grid scale, there is some possibilities that you could see hydrogen, and also there are other chemistries besides hydrogen. Ammonia is one of them. You could use electricity to make hydrogen, and you still have the issue, though, of storing that much hydrogen. You typically, in order to store it, you have to compress it. You also have some issues of if you're using electrolysis to make hydrogen, your round trip efficiency is much worse than, say, for example, with lithium. The fuel cell alone is 60% efficient. So by the time you electrolyze at 60% efficiency to store it and compress it and then take that energy back out and back through a fuel cell that's only 60%, the efficiency gets to be very, very low for that. But in many cases, that still is quite tolerable, where it would be better than curtailing wind or curtailing wind or solar outright, where you're just wasting the power. You could certainly look at some options for that. You also mentioned carbon capture. Carbon capture has some possibilities. There are they're probably most practical in a integrated combined cycle gasification type of network. There are a few new fuel cycles. I think it's one called the alum cycle that have the possibility of kind of basically being able to consume hydrocarbons and a bit more efficiently making power and capturing the CO2. But generally that adds to the cost of that, but it certainly could be an option because it's so difficult to scale up the resources of solar and wind to that level of scale.
Wow. Yeah, the economics are kind of fascinating when you mention that there's an inefficient, tortuous path for hydrogen, but if you're in a remote solar field where the marginal cost of energy is nil or next to it, and you have more power than you know what to do with, that might actually make sense. And that's
Sure.
That's the dynamic you just have not seen till now. So that's
yeah.
fine.
Well, there's been a lot of effort, to improve that calculation. There's the acronym LCOE, levelized cost of energy, to help to try to take some of those things into account. But obviously, if you have specific situations, for example, in China, in the Mongolia area, they put in massive amounts of wind, but they put so much wind in that they found they were curtailing it 15 or 20%. And that was a situation where they said, well, we need to put 100 megawatt vanadium redox flow battery. I'm not sure if that battery is operating yet, but they basically thought they could significantly reduce curtailment because they're just dumping that power. They're just wasting 15% of all the wind turbines they just put up.
Wow. What does curtailment look like, actually? How do they physically curtail power?
So the electric grid suddenly has way too much power than they need. So they're basically saying we need to, has way too much load to be able to let me see how I can explain this. Electric grid operator, an ISO, could suddenly have way more power than they need for the loads, all right? In which case they start to back off all of their generating capacity, but they can't back off a nuclear plant. Nuclear plants run steady. They can only back off coal plants so much. And even natural gas plants have to stay running. They don't have a huge turndown, so they still have to run at some fraction of their full-scale load. And basically, there's tons of solar and it's a windy day too. Somebody's got to shut off power because there's nobody consuming that much power, and ISO will issue a command. And as I think that every one of these assets that is an ISO registered asset must have a point of connection and a responsible entity that can shut that load off. And in fact, even our wind turbines in our local town, from time to time, when the local marginal price went negative, we were fined $15,000 just for running and generating our wind. We now have that under a much more sophisticated control system where we have somebody watching that 24/7, and they will disconnect that load. And even though it's windy, we stop generating.
Wow. Yeah, these are issues that didn't really exist 10, 20 years ago.
Well, I mean, the grid problem of balancing always existed. You still always had the issue, but with large generating capacity, they kind of solved it with with spinning reserves and there always was a complicated automatic generation system. But the whole issue of base load and spinning reserves is being served by different types of entities today. So it is definitely seeing a lot of changes, and a lot of people didn't realize that these kind of changes are occurring. Certainly the people that operate the grids and the grid regulators throughout the world have become very good at this. China has become very good at this with such a huge grid expansion that is underway there and also in India.
Well, Rick, it's been a great hour of just very fascinating information. Do you have any last thoughts that you'd like that perhaps subjects we didn't cover? I know you and I before our recording today, we talked about participation from smaller players for demand response applications. Would you like to address that or anything else?
Yeah, I'd like to give just an idea to give a little bit more of a futuristic view. As an electric car owner, I would like to be able to participate and help my grid, but I'm not kind of allowed to do that. And I've been talking to a few aggregators out there, and that are trying to get involved with a number of smaller players. I talked to a small company called Ohm Connect in California. They bid into some of the wholesale energy markets. And they have 100,000 individual customers that are residential customers, and they basically have developed an iPhone game-like app so that all of these customers will suddenly get a text, 2 hours from now, peak load is likely to happen. We need you to conserve power. All right, and they play this thing like a video game because now they're competing with neighbors, competing with other groups of people, and they gain points by going down and turning their air conditioner's throttle set point down, or deferring charging of their electric vehicle, or shutting their hot water heater off. So they basically accumulate these points, and if they're really at a situation where this is the one peak hour, they get bonus points, and so they encourage people to participate in a demand response environment as a video game. And at the end of the month, the aggregator gets paid by the utility by demonstrating that he has in fact reduced load, which is verified by smart meters and a base calculation that shows each one of these players in fact gained points based on reducing power from their base load over the last year. And I think you're going to see a lot more of this in the future. This is relatively rare here. We don't have that doesn't happen in very many locations yet, and it's still very early in the development. But I think there's a lot of space and room for aggregators to interact with the larger number of users, smaller users at the residential and small commercial level, and make it fun to play this game and help the grid be stable at the same time.
Well, Rick, that's fascinating, that gamification approach to that. Recently, Edward and myself were on a call with an operator of an electric vehicle charging platform, and they've begun going out to the energy market and bidding for power, and they're going to be a power aggregator and distributor to their own EV chargers.
Yeah, absolutely. I think EV, the projection of EV sales vehicles. You look at, there's an awful lot of electric vehicles suddenly starting to come out. All right, we're seeing every major vehicle manufacturer making a relatively serious commitment toward electric vehicles. You certainly see it with Volkswagen following their diesel scandal. Mercedes is there, Volvo's there. Obviously there's established players like Tesla and Nissan that are out there, and the Chevy Bolt. So we certainly see that these electric vehicles are there. There will become more opportunities with that much energy storage driving on the highways and parked at night unused, and some of the other issues of autonomy of those vehicles. There's going to be a lot of opportunities for them to participate in the future. Right now, most of them, there's no opportunities. They come in, plug it in. They don't. The fact that they're plugging in at peak load, and costing their local distribution system money because they increase their peak load. The distribution companies have yet to figure out how to incentivize them and fairly incentivize them to be part of the electric grid management. And certainly, if you can make it fun with a video game, that would be a lot more fun than, because most people are just not looking at their electric meter. They really want to just take that electric power for granted and ignore it. But I would say there's one other statement there. That's to make it fun and to make an economic incentive. Voltage moves electricity, pressure moves fluids, and money moves people. And money with a game incentive is even better.
Wow, that's a great end note, Rick.
I like that. I like that a lot, Rick.
That's great. Well, Rick, we're up at the top of the hour. This has been a fascinating discussion with you. Expect to be invited back. And to those listeners out there, keep tuning in for editions of the ARC Smart City Viewpoints podcast. And if you'd like to reach out to ARC, we're online at www.arcweb.com. Feel free to contact Rick or myself, Jim Frazer, or Edward Fidler. And I'd like to put out a thanks today also to our sound engineer, Tom Cabot, who's in the background processing things today. We look forward to seeing you all again on a future edition. Thank you very much for attending today.
Great. It was great fun.
Thanks so much, Rick.